Equipment wrecked radio. And by the way, Bob, I'm not saying you did, but some of your mastering guys have wrecked source material. Loudness is not a bad word. It really isn't. If you apply it properly, or apply the stuff to get loud properly, you can be as damn loud as you want and sound. How many of you have been to a concert where it was done right and it was loud and it sounded good? I have. I've been to a lot of concerts to where, you know, I'm glad I had the ear, you know, the things for my ears. But I've been to some that sounded really good. Actually, and one of them, believe it or not, was a Who concert on account of the fact that Pete Townsend, you know, suffers from tinnitus. And when they did that reunion thing in 1989, they had to, his doctor said they could only keep a sound pressure level. They couldn't go beyond a certain point. Well, and I saw them a number of times that tour. I saw them at Radio City Music Hall, saw them at Cleveland Stadium. It sounded amazing. It was loud, but it was beautiful. You could hear detail. We can do the same damn thing. Sorry for the, you know, four-letter words. You can do the same thing with audio processing. You do the same thing in mastering too. It all comes down to what we're doing, how we're applying it. And you know, that the days of it has to be, you know, what I call that moment-to-moment loudness, you know, louder than the next guy. Doesn't always have to be. Let me use the analogy. Remember I was talking about the analogy about the hot water? It's the same thing. I've heard radio stations. As a matter of fact, we were at NAB this year, we showed a our own modulation monitor that has a loudness monitor in it. And one of my little brothers in the company, Leif Clayson, the developer of the Omnia 9, there's another sharp cookie. Leif was, you know, saying, look, this is louder, this is louder. I said, whoa, slow down, Leif. Just forget about the numbers. The number shows it's louder, but to my ears, the other one sounds louder. Why is that? Because the other one, the ears were breathing a bit. Now, why am I using that hot water analogy? Because when you get something dynamically loud, all those moments to moments of loud, you hear the ears can breathe a little bit. That's when you're hearing loudness. If you just crank it up to where it's tight all the time, yeah, the initial moment might appear loud, but once the ears desensitize, it doesn't sound as loud anymore. I've set our stuff up to where the guy up the dial might be density-wise, might be signal level-wise, electrically, that's what I want to say, electrically louder. But the perception was the other one was louder because the ears could breathe a little bit. And thankfully, I think more people today are starting to understand this. When I say people, I mean management types, programming types. You know, the day of where, you know, the mod monitor looked like a current meter on the transmitter, right? I love this crowd. You guys understand, you know? Those days are over. I mean, we can do it. You know, sure, we can do it. But it doesn't have to be. You want it to breathe a little bit. So, how do you get loud? If you choose to do so. Start with clean audio. Again, I mean, you know, garbage in is more garbage out. Again, you know, coded audio, if it's at a low bit rate, you know, you're going to be in trouble. You know, I think a lot of these, again, it sounds simple, but you add all of this up, and you know, you get the right setting, or you get with the right individual, if not yourself, to get it there. You know, if I may say so, then you'll have a weapon on the air. You know, the first ad I ever ran, you know, I didn't have a lot of money. I took a little ad out in Radio World, and you know, the first product was a modified Aphex Dominator that I called the Vigilante. I know it's that Italian mafia thing. But the first ad said, start taking hostages. And the reason being is if you get it tuned up just right, you've got a weapon. And you know, I mean, I had to laugh in a healthy way when the program director at a classical musical station, he's not competing with the rock guy, but he had to drive home that night with some added testosterone because he's thinking like, Beethoven is really giving Springsteen a run for his money. You know? I mean, it's true. So, but again, we did it carefully. We, you know, we paid attention to detail, and it, you know, it's actually I have their preset, and I've been so busy the last couple of weeks. I've been wanting to put it in the unit on my bench, and then like run it with rock music through it, because who knows? You know, we may be onto something there. So you know, again, this may sound crazy, but it is true. Have fun with it. You know, I mean, I take a lot of pride in this work. I took a lot of pride in my days in radio. I was proud to know that when I hit 100.3 in New York or 100.7 in Cleveland, we're the best. But I had fun doing it. You know, some of this here is if any of you guys have questions about it, I'm sure we'll have time for questions and answer later. But you know, I think I'll kind of move on. At this point, any questions from anybody? Okay. New FM limiting method. Why does it go to 11? Hence the name. You'll see I probably owe Scott a few royalties here. You know, if it's too loud, you're too old. How you doing, dude? This all came about because at the time, it was my view that modern processing was reaching extreme levels. It was loudness at the expense of quality, more loudness than allowed by law. And I'm not saying just overmodulation. I mean, it was over the top. You know, we can get into the whole record industry and things of that nature. And deep down inside, it was becoming an annoyance for me. And what ended up happening, true story, was we were doing a 10-year birthday celebration for Omnia. So this would have been 2007. I was being interviewed by one of the trade publications, and they said, so what's the future? You know, you guys have kind of become the kingpin now. You're celebrating 10 years, and you know, worst, you know, and as I said, I got to go from worst to first, not once but twice. Once with Z100, and then doing this audio processing thing. And so I made a bold statement that at the time I didn't have, you know, it's kind of like when Pete Townsend, if you ever heard the story about how Pete Townsend wrote Pinball Wizard, he had Tommy basically done. He did not have the song Pinball Wizard. And their manager said, we've got a guy, Nick Cohn, who wrote for the New Music Express. He's going to interview you Friday night. You got to meet him at this pub. And oh, by the way, he's a pinball fanatic. So Pete meets him, and the guy's playing pinball. And Pete's telling him about this deaf, dumb, and blind thing, boy, Tommy. And Nick says, well, what's so special about him? And Pete says, well, he's a wizard at pinball. And Pete did that because the guy was playing pinball. He never had the song. So he invited the guy to come to their recording session in 2 days. Pete ran home that night, drunk as a skunk, and wrote the song. That's how the song ended up in Tommy. I mean, think about it. Deaf, dumb, and blind, pinball, doesn't make a lot of sense to me, but, you know. But in any case, so I'm in this interview, and they said, well, so what's, you know, so I'm thinking like Pete Townsend. I said, well, the next step is we have to sound cleaner. We have to be just as loud, but we have to be cleaner. I'm thinking, okay, bud, you know, we're always, Steve and I, our motto has been to raise the bar. Now I'm thinking I've just, you know, put the bar 50 yards out there. So, but I will say that even in my ears, we'd reached a point of what I felt was no return. So what I did was, you know, and that, yeah, a lot of your programming people, you know, they want to pump us up. So the challenge and a promise. And, you know, I said to myself, we're going to, whatever we do, it has to sound cleaner. So put quality back in the on-air audio, maintain competitive levels of loudness, whip up a new algorithm. Yeah, you know, we joke around our office, oh, it's just a few lines of code. You know? That's true. Oh, just a few lines of code. You know, Steve used to say, oh, it's in the can. Yeah, right. So what I did was this, at the time it was a 2-year research project, and believe it or not, I've updated it about 1.5 years ago. It's probably some of the most exciting work I've ever done. The results were quite revealing, and the rest of the, well, not the rest of this presentation, but this next part is going to be along that journey. So what I did was, you know, hot rock and flame throwing, you know, it was pretty annoying. And I will tell you, it was a very humbling experience. What I did was I went away from it. It was around Christmas time. I went away from it for about a month. I didn't listen to the radio. I didn't listen to stuff in my office. I came back to the office and I put on, it was Omnia 6, and I'm listening to it, and I was not a happy camper. But by the same token, I'm not one of those, misery loves company kind of guys. It's not that I was hearing anything any better from anyone else. But I said, but we're not a Me Too company. We have to raise the bar. So to me, yes, we have to deal with the modern music mastering. Hopefully it'll get better, but it's a fact of life. To my ear, the bass was very rich. A lot of presence in treble. There was a synthetic tonality to it. The high frequencies were overly bright and harsh. The bass was tightly defined and sometimes distorted. The distinct annoyance I was hearing, and the song that was brought to my attention, which was by one of our customer support guys, Mark Manolio. Mark's got a great set of ears. I love him dearly. Can be a pain in the you-know-what, but this is how stuff like this comes about. Mark brought me this song by Kelly Clarkson called, the name escapes me now, something, you guys are going to hear it in a few minutes. And it was a piano. She's humming over this piano, and her voice is sounding, like it's frying. And this sizzling bacon frying thing that I was saying to myself, I was hearing on other stuff. All of these items I was hearing this. When I say equal opportunity offender, I was hearing it substantially worse on some competing products. But again, I can't just use that as an excuse and say, well, we're less offensive. I did notice, though, that when I reduced the clipping, the problem would go away. So I was saying to myself, is this the age-old problem of too much bass causing IM distortion? Oh, because of you. But I'm thinking, wait a minute. Because of you doesn't have any bass. She's humming, and there's a piano playing. This is a spectral picture of the song. You can see there's next to no low end, some of the piano, predominantly her voice, and maybe some of the upper registers of the piano. I believe, if I've not screwed anything up here, okay. This is the source. It's done on a loop. Give you an idea, this should be the first one. It's pretty obvious. There'll be two sources. One of them's our product, by the way. You got the picture, right? Okay. I think I mentioned no bass in the segments, sizzle remains. Now I'm like, what's going on? Same result with, and believe me, I tried ours, I tried the other product though, I tried a whole bunch of others. They all did it. Thinking, all right, and now I'm getting excited because it's like I got something to, but it's that challenge. It's like, what can we do here? So it's like, well, I guess we're gonna have to probe into the clipping methods. Some people call it distortion control, some people call it distortion canceling. We've probably pushed the cancellation means beyond their capabilities. So, as a quick refresher, if we look under the microscope, before you're asking about the limiter thing, here's a perfect example of zero attack time, zero release. This is clipping. And that's on the oscilloscope, and then this here is all the harmonics that we get from it, okay? This is an example of a 1 kilohertz signal. Now, we can do some static functions to suppress some of that harmonic stuff and still get away with the clipping. But what happens when we bring in added harmonic spectra? So I came up with a test that I call the clipper-induced intermodulation distortion test, where instead of just looking at, let's say, one frequency, let's take a low frequency, like 100 hertz, and then let's sweep Let's hold that 100 hertz into clipping. Then let's add 5 kilohertz and then sweep up to 15 kilohertz and employ 75 kilohertz preemphasis, because that's very, very important here. Remember I was telling you guys about that, how much that preemphasis boost gain is. And let's see what happens. Well, what I found was, here's an example of 100 hertz and 10 kilohertz. Technically, you would see just the fundamental at 100 and the fundamental at 10 kilohertz. Well, all this stuff in here is intermod based on the clipping. Now watch what happens. Here's a sweep from 5 kilohertz to 15 kilohertz. You know, we're holding steady on the 100 kilohertz tone. And as we go up in frequency, see all the stuff that's coming in here, this is clipping-induced intermod. I'm thinking to myself, wait a minute. I think we're onto something. This here could be all the egg frying business going on. So, as they used to say in Mission Impossible, so your mission, Frank, if you choose to accept it, is how do we, you know, do this and this, but get rid of all this stuff here. Hence began 2 solid years of this. This is all I did. So what happens with many signals present? The sizzling stuff, not good. What I found was we pushed the levels. We'd reached the point of no return in the static method of doing distortion, cancellation, or suppression. And basically what ends up happening is we have some masking filter that under certain conditions we're able to eliminate distortion, but as we heard just a couple minutes ago, there's other distortion that comes through. Intermodulation, which was the stuff, is random spectra. If we've got a static filter, what's going to chase this random spectra? Here's the problem. It's running around. We've got to be able to come and get this and get rid of it. So, such that the static approach is not sufficient. And a lot of that comes back to the filtering topology, what I felt was the weaknesses in the filtering topology. So some people will say, well, you know, just throw more bands of processing at it. Well, it's not the answer. It's a waste of DSP cycles, MIPS, and marketing. You know, I really laugh because it is marketing rhetoric when somebody says, oh, you throw all these bands of processing at it and it's going to sound great. Well, what I laugh at is that all the bands of processing, they threw it in the limiter section. And that's not the loudness generator. They threw it, if they threw it at the AGC section, it might make a difference. But we have found that once, you know, the point of no return or the point of difference, once you get up 4 or 5 bands, you start adding more to it, there's really not much gain. So to me, it's marketing rhetoric. Some folks have gone after it using what they call multiband clipping. The problem with multiband clipping is it does not take into consideration any interactivity of outline spectra. Point being is, when we had the scenario with the 100 hertz and the 5 kilohertz, multiband clipping can't understand what's going on in between there. And we need to be able to get in around there and make adjustments. So the answer ended up being first understanding the induced intermod from harmonic distortion and the range of spectra that is generated by both of them. And the important part is being able to generate an adaptable means to suppress both of the problems simultaneously. Now, how we go about this without getting overly scientific is the way we eliminate overshoots in low-pass filters based on something called the Gibbs phenomenon. Gibbs phenomenon, believe it or not, was discovered by a physicist by the name of Gibbs at Case Western Reserve University in Cleveland. It's this phenomenon that enabled, understanding this phenomenon that enabled Bob Orban to get around the overshoot problem in low-pass filters. There's also ways that we can take advantage of this phenomenon to suppress distortion. What I learned, and believe it or not, this comes from the land of the codec. The ear picks up distortion of the harmonics that are the furthest out from the fundamental distortion. Now, why would I say that it comes from the codec? what does the codec work? Is it has a masking, an adaptable masking filter that walks around, and it's throwing away far out, lower level signals, and then, the ear doesn't perceive that. We applied some of that same thinking to all the clipping products. Well, look what happened. Here's the before and after, 100 hertz and 7 kilohertz before, and here's after. Now watch what happens. We came up with this thing that we call the low IMD clipper. It's, to me, the biggest challenge for the processors. The goal, preserve quality, clarity, and loudness. It's different than any other prior canceling mechanism that is used to suppress distortion. And basically what we're doing is we're putting some of the delay through the system to work as compared to just having some static function that's there. Again, if we give away the secret, well, there's different ways to deal with these things in different parts of the country. Okay. Here is the blue is the old method, and the yellow is the new method, running that same test that we ran before. Watch what happens. As we're going up in frequency with the yellow one, all that intermod in this section isn't, later on you'll see a little bit creep in, but it's way down there. But all this stuff, this here's the stuff, the annoying stuff that would cause the sizzling. So we're going to welcome Kelly back. Greatly improved. This was when I first designed it, and I have it even better today. This is with 2 dB more clipping. I mean, it's hammered hard, but the frying is basically gone. Okay. Now, what we learned here is more than just in the clipping, and it applies actually to the rest of the processor. First of all, the answer lies not in the number of clipping bands and filters, but how the distortion products are dealt with interactively on an instantaneous basis. You want to, some of the people that are out there with a whole bunch of bands, they could put 3,000 bands up, at it, and they're still going to fry eggs with Kelly Clarkson. Multi-band, or 5 and 6 bands, it's not the answer. As I mentioned before, multi-band clipping doesn't take into consideration the interactivity of outline spectra. That's where those methods, they eventually fail. The proof is in the sonic performance of the content. What we learned was if we're able to suppress intermod distortion in a clipper, Corny and I took that same philosophy and thought, well, in a dynamic limiter, which on its own is going to generate intermod distortion, what if we apply some of that same thinking to a dynamic limiter? And the amazing result was we were able to get the dynamic limiter to be do its work and sound smoother, cleaner yet. So the work that we ended up doing on the clipper has been far-reaching in not just clipping, but limiting, look-ahead limiting, and in many aspects of our current generation of products. By the way, I've run Kelly Clarkson in the 11, and I've run it in the current version of all our competitors' products, and we're the only one that doesn't. Well, I should say the Omnias are the only ones that don't. The Omnia 11 and the Omnia 9 don't fry eggs. This here I wanted to share because this here is an old screenshot, and it's now in something that we'll have as a product later this year. It's still available by way as a device, an app you can run on the internet, from the internet, called MPX Tool, developed by my buddy Leif Clayson. And to give you an example, we're today here. We can have a scope view, look at levels, left, right, composite, but we also get a nice spectral analysis of the composite signal. And believe it or not, when I was talking about composite clipping before, in the old days of composite clipping, if you pushed the composite clipper, you'd start to get a lot of junk in and around the pilot. And if you got a lot of junk in and around the pilot, what a lot of radios would do is they would falsely go to blend, because some car radios, the blend circuit is triggered by how much noise is in and around the pilot. Likewise, you know, your RDS and SCA range could get annoyed with, but we're now able, if somebody wants to use composite clipping, we keep the pilot, you know, perfectly clean, as well as the rest of the spectrum. So, up to now, we've talked a lot about audio processing. How are we doing on time here? Oh, it's getting a little after 11. When I say we talk about processing for coded audio, I know that a big feature about today is to talk about HD radio. A lot of the RF parts and encoding and the importer exporter part, I know Jeff's going to handle this afternoon, and so I'm not even going to go there. I'm going to stay in the audio processing realm with regard to the various things that need to be considered, things that apply. We'll talk about some algorithms, have some other audio samples, and then when I wrap up, I think will be time for lunch, or probably questions, and then time for lunch. So, traditional processing. Again, I use this term, processing for static functions. Traditional transmission paths have used a singular, one-dimensional functions where the target's been known, and the audio processor is designed to accommodate those known functions. You know, think about AM, think about FM, think about television. Coded audio, HD radio, to me they're one and the same, all apply. You know, we have precision peak control, bandwidth limiting based on whatever the range is, normalization, and in the case of FM, stereo generation. There was a time in AM where we talked about stereo generation, but that's kind of gone away. So with HD radio and multicasting, broadcasters need new audio processing tools and technologies. They need the processing tools that have intelligence for spectral density management, distributed look-ahead limiting, dynamic program-dependent codec provisioning capability, because, you know, in broadcasting, there's never really a free lunch, you know. In FM, our challenge has been the pre-emphasis curve. You know, to be able to have this spectra that, you know, has this major tilt at the high frequencies, be able to get it through that small pipe, remember the funnel, and have it come out to where we're not frying eggs. There's a challenge there. Well, on the coded audio side, obviously people want to shove, you know, the best quality down the smallest pipe possible. You know, theoretically, if you're just running one stream over the air, you have 192 kilohertz of bit. No, it's 96. Yeah, I'm sorry. It's 96 of data, and you know, the codec for that, you know, that's chosen works fairly well, but there's still things we have to give consideration to. So again, we're going to come back to the audio processor as having it be a tool, so that we're going to be able to provide the best sound based on the bit rate that's needed. The codec, you know, independently of what you may think of coded audio, it is here to stay. I mean, you know, we all carry some form of mobile device. You know, now the next step is that we're going to be able to listen to the radio on it. You can pretty much watch television on it. And the key is being able to provide quality at lower bit rates. But in order to do that, we have to have an understanding of the coded system and what must be applied to ensure great results. And as my Sicilian fathers told me many times, Frankie, when God gives you problems, you make lemons out of lemonade. So the key is to pack the pipeline. You know, data-reduced audio systems, they've changed our world. The payload that once carried stereo now carry multiple streams, and it can even carry surround. You know, Steve and I, it was probably about 10 years ago, we you know, we still have all the tech. For whatever reason, the industry didn't want to get involved with it, but we even showed a way to do discrete 5.1 surround on FM using the HD radio system. And if we wanted to, we could even, you know, embed that into the FM stereo system and do surround sound. And, you know, one area is that the codec developers continue to raise the bar. You know, some of you may or may not know, it was 1992, and the first people to bring ISO MPEG Layer 3 audio coding into the US, basically MP3, was Steve Church. He was the first licensee for the Americas. It went into the original Zephyr, and you know, at that time we're thinking, wow, 128, you know, on an ISDN line, this is amazing sounding. And now, you know, we walk around and we listen to stuff at, you know, 32. That's, you know, I don't want to say it's amazing, but at that time, could anyone have thought that we could get stereo, you know, let's say transistor radio quality stereo audio at 32 kilobits? You know, even the guys at Fraunhofer would have said, you're crazy. Well, you know, even they raised the bar. Codec developers, they're on a fast track. You know, it's easier to improve the payload as compared to expanding the pipeline. We'd all love to see the internet, you know, increase its payload size by a factor of 10, 100, or 1,000. It's probably not going to happen, or if it is going to happen, it's probably not going to be in my lifetime. But lower bitrate codecs have resulted. They are much more fragile, more susceptible to artifacts, distortion, etc. So as you can see, you know, our challenge keeps going up, and you know, the key is, what are we going to do about it? Now, what I'm going to talk about today came out of some development we did a while back, which was what could we do with regard to getting a very low bit rate to sound as good as possible. I realized that, you know, HD radio, you can run one stream at a higher bit rate and sound, you know, sound very good, but I also know there's broadcasters that want to have, you know, 2, 3 streams out there, and as you know, cut up the pie, you've got more challenge. So the key again, because what was happening were people were taking conventional limiters, they're trying to use modified broadcast audio processors, and the end results were not all that appealing. So again, some new thinking / algorithm was needed. So we're going to talk about an enhancement that uncovered some negative discolorations that were affecting the presence in high frequency, what I'll call weirdness, and yes, there'll be more on this a little bit later. The history, I think I touched on a little bit of this, no free lunch. As you know, if I can borrow back from the previous part of the presentation, let's understand you know, let's figure out what the challenge is and then alleviate it. You know, by example, the whole how we deal with FM stereo, preemphasis, and low-pass filtering. And speaking of FM, there are reasons why conventional FM audio processing is not recommended for coded audio. One, we've got generally that preemphasis curve embedded, so you know, trying to shove a whole bunch of added high frequencies through the system, even if we roll them off, doesn't help. And we've learned that trying to run clipped audio, hard limited audio through a codec doesn't work real well. And you'll see some screenshots later on as to why that is.